So last time we were talking about the pointwise convergence of the Fourier series. So just to remind you of the notation and the result we're trying to prove, basically here we have the partial sum of the Fourier series. That is, if you take a limit and send capital N to infinity, then this partial sum will become what we call a Fourier series. So now the result we're trying to prove is essentially for any point x sub 0, we want to show the Fourier series, which is right here on the left-hand side. You should think of this as the Fourier series. This is the Fourier series right here. Yeah, it took me 6 minutes just to write FS for Fourier series, in case, And then we want to show for each x naught that it converges to this. So this is called the adjusted version of the periodic extension of F. You should think of this average as just what we call F tilde, F bar tilde. Of course, what else would we call it? F tilde is the periodic extension part. F bar is the adjustment, where we're averaging either at removable discontinuities or jump discontinuities, but then we drop the bar. Okay, so you can think of this entire side as just being F bar tilde of x naught, but then we drop the bar. So we're just going to call it F tilde of x naught, with the understanding that that's the adjusted version of the periodic extension. All right, so yeah. So the way the proof works is I want to write the partial sum and F tilde of x naught as integrals, and then look at their difference in an integral, and then use a result called the Riemann-Lebesgue lemma, which is for certain types of integrals. It's for integrals that have a function times a trigonometric function. And we have this idea of oscillatory cancellation that this Riemann-Lebesgue lemma, establishes and allows us to take advantage of. So essentially, the first couple of steps of the proof is just to rewrite the partial sum of the Fourier series and its target function, F tilde of x naught, in integral form. So initially, we're just doing, so you can recognize this term as sort of a generic term from a trigonometric polynomial, such as the type that the partial sum of the Fourier series is. And here we're writing this generic term of the trigonometric polynomial as an integral. And you can ignore all the junk in the middle, because that's just integral properties and trig identities, nothing really deep happening, just notationally, annoying. So the point here is now, our first waypoint of the proof is when we're able to write this first partial sum as an integral. So here you really want to see at the top here, it's written as a sum, and you can ignore all this stuff in the middle. That's just some kind of pushing symbols around. So we can ignore this stuff here, and then just go down to this last equation here. And, the point is, at the end of the day, say, what's the point of all this, mathematical gyrations? The point is now we've written the partial sum in integral form. So that's step one. The other thing we want to do is write the target function. So remember, we want to now write F tilde of x naught, which we're claiming the partial sum will converge to. We want to write this in some kind of integral form. So I'll put a question mark here. And so that's the next step. So, we've succeeded in writing the partial sum of the Fourier series. That's supposed to be a check mark, but here we go. We've succeeded in writing the partial sum of the Fourier series as an integral. So now let me write the target function F tilde x naught as an integral. Well, how do we do that? Well, it turns out that the properties of this thing here that we're calling the Dirichlet kernel, it turns out we can use the Dirichlet kernel to actually accomplish this feat. that is writing the target function as an integral. So that's what we'll do. So first, let me tell you the properties of the Dirichlet kernel that we like that allow us to do this. The first property that we like is that this, Dirichlet kernel 1 over L of this integral integrates to 1. And you go, well, why do we like that? Well, we like anything that integrates to 1 or sums to 1 because we can do this sneaky trick where we just multiply by f of x. Yeah, I'll try that again. We just multiply by, here we go, be the letter, be the letter, be the letter. Oh, there, it's not bad. Be the tilde. There we go. If you put your whole body, mind, heart, and soul into it, you may be able to write on Zoom. So here, I'm just going to multiply f tilde x on both sides, like, very sneakily. And because f is a function of x, and we're integrating with respect to u, on the left-hand side over here, I can bring the function inside. And on the right-hand side, on the right-hand side over here, you'll just have f tilde of x equals, and then some integral expression. So that's one sneaky thing of the Dirichlet kernel that we like. The other thing we like is we can write the Dirichlet kernel in this form as a quotient of sine functions and say, why is that important? For the Riemann-Lebesgue lemma, what we need is an integral of a function times a trigonometric function that has a wave number. And so the second property of the Dirichlet kernel is extremely important because if you look at the numerator here, it's a trigonometric function with a wave number. All this constant in the front, is a wave number that changes with capital N. Because eventually we take a limit and send n to infinity. And the Riemann integral, the Riemann-Lebesgue lemma needs an integral of a function times a trigonometric function where the wave number, is going to infinity. So that's the other part of the Dirichlet kernel that's, awesome. So now let's write the target function as an integral. So remember, we've already succeeded in writing the partial sum of the Fourier series as an integral. And that's what up there is, that was our first waypoint that we were happy about. So I'll go ahead and put the check mark next to it. That's what we were looking for. Now, the second thing is to write the function. So now here I use this property that the Dirichlet kernel integrates to 1. I'm going to use this property, multiply both sides by f of x. So here you have f tilde x being multiplied to both sides. And so now look, we have our target function in integral form also. Let us rejoice. So now we want to form the difference, the partial sum minus the target function. And eventually, remember the end goal is to send this n here to infinity and conclude that this difference is going to 0. That's the end goal. But look here, by the end of this slide, we've succeeded in writing the partial sum of the series minus our target function in integral form that's actually in a Riemann-Lebesgue lemma friendly format, where it's a function times an oscillating wave, where we can send the wave number to infinity. So just once we rearrange this integral, so here I take this sine term and move it below this difference here. And so now that becomes a function I'll call q of u. And the function that's left on top here, this sine of n plus 1/2 times pi over t minus x naught, that I pull out, and that'll become my oscillating wave part of my Riemann-Lebesgue lemma. Remember, the Riemann-Lebesgue lemma is all about oscillatory cancellation. So I need a function times an oscillating wave, and then we're going to send this wave number. We send n to infinity, but if n blows up, m blows up. So we send m to infinity, and then, according to the Riemann-Lebesgue lemma, if q of u is piecewise smooth, then we have oscillatory cancellation. The integral goes to 0. And remember, the integral here is equal to this difference. So if the integral goes to 0, this difference goes to 0, then we've just proved that the Fourier series is converging pointwise to f tilde bar of x naught. So that's kind of how everything fits together, thus far with this proof. And so now there's only, if you accept that Q of U is piecewise smooth, if you say, I have a lot of experience with functions, and looking at this function, it's piecewise smooth, and I believe that, then we're essentially done with the proof. And so, now there's one final irritating detail, and I don't even know why I'm doing this, but I guess it's because it's a math class and it's an analysis class, so we should probably do some of that. The final detail I'm going to do is I'm going to just show you now that Q of U is piecewise smooth. And then the Riemann-Lebesgue lemma kicks in, and we have pointwise convergence. And moving forward, we get this result for free. Was there a question?
Yeah, sorry, didn't mean to interrupt.
No, you're fine. You're fine. No worries. Go ahead.
So for this to be piecewise smooth, we can't have our numerator go to 0.
Well, here I'm more worried about the denominator going to 0.
Oh yeah, sorry, that's what I meant.
Yeah. So now I'm going to investigate the behavior of the function at the roots of the denominator with a limit, and make sure it's not an infinite discontinuity. That's what I now really need to do.
Okay, thank you.
Does that make sense to you?
Yep, thank you.
Yeah, of course. So for piecewise smooth, now let's review very slowly. Piecewise smooth means the function Q of U is piecewise continuous with no infinite discontinuities, and its derivative is piecewise continuous with no infinite discontinuities. Looking at the function Q of U, it's a quotient function. It's a function with a numerator and denominator. So really the only part of this function that I'm worried about is when the denominator is 0. Away from 0, the numerator is a piecewise smooth function. The denominator is a piecewise smooth function. The quotient of piecewise smooth functions will be piecewise smooth. Away from the roots, where the numerator and denominator are well defined, there's no problem. The only place we're worried about is where the denominator is 0. So now the next 2 slides will address, just take the limit at the roots of the denominator and show you it's not blowing up to infinity. So here, removable discontinuity or jump discontinuity is allowed. What's not allowed is infinite discontinuity. So I just have to now show you there's no infinite discontinuity at the roots of the denominator. So I'll first show it's piecewise continuous, and then we'll talk about the derivative being piecewise continuous, and then we'll have that it's piecewise smooth. And here, with quotient functions, in general, quotients of continuous functions are continuous on their domains. So here again, I just want to check what's happening at the roots of the denominator here for the Q of U function. So I've broken this up into 2 cases. So first, I want to just restrict my vision to the closed interval minus capital L to L and justifying this result. So here I say without loss of generality. What that means is I haven't imposed any further restrictions, and I haven't made any new assumptions. That this assumption I'm making is an assumption that's allowable and will not in any way hinder the generality of the result that we're about to prove. And the reason it's okay for me to make this assumption is because of the periodicity. The logic here is that the function f tilde bar Q of U, both functions are periodic, the numerator and denominator here of Q of U. So Q of U is a periodic function. So it'll behave the same on the interval minus L to L as it does anywhere else, because it's periodic. So we're just going to observe the behavior in minus L to L. Since Q of U itself, being the quotient of periodic functions, is itself periodic. And again, for that, we break that up into 2 cases. This is how every analysis proof goes, where you always go very slowly and you break it down into cases. That's a very fundamental strategy in math in general, right? So here, I'm going to look at when x sub naught is inside the interval, properly inside the interval, versus when it's on the boundary, when it's, equal to negative L or capital L. So case one, I'm looking at the case where X naught is properly inside the interval. And here I say, since U, so this very first step, I want you to just stop and think about. Okay, so let's slow down right here. I say U is in the interval minus L minus X naught to L minus X naught. So how do I know that? Okay, so here, let me backtrack here. So I want you to look at this integral. In this integral, the U variable is going to be in between minus L minus X naught and L minus X naught. Okay, and I only care about U in the context of this integral. So in the context of this integral, I can assume our U variable is between minus L minus X sub 0 and L minus X sub 0. So that's where I'm getting this statement right here. Okay, and so we're gonna use this again. So you're gonna just keep that in your back pocket. Where did we get that from? It's from the integral. We're integrating U between these two bounds in the integral on the previous slide. Okay, so my claim is because X naught is inside the interval, properly inside the interval, and U is in this interval, for this particular case, and I'll do some math here, so just hold on for 1 second. For this particular case, the only root when we're properly inside the interval is when U equals 0. That's the only root for this case. So hold on, let's just think about the math now. So if you just focus on this function, okay, look, for example, if this number here, if U, so let me cover up U. So if U here were equal to 2L, for example, 2L, then the 2L's would cancel and sine of pi would be equal to 0. But to get a 2L here, if you wanted this to be equal to 2L, here we'd have to have L minus L. So the only way I could get, for example, U to equal 2L in this, where U is in this interval, if X naught were exactly equal to negative L. But if you look, X naught in this case can never be exactly equal to negative L. So U, for example, can never be equal exactly to 2L. That's where I should have said, for example, 2L. And so here we can prove, because of the restriction on X naught, the only place the denominator will be 0 is when U is 0, which is, of course, in the interval. 0 is in the interval, obviously. Again, you could say, well, what if U were negative 2L? In that case, the 2L and the negative, and the 2L's would cancel. I'd have sine of negative pi, which again is 0. But for U to equal negative 2L, X naught here would have to equal L. That's the only way you get a negative 2L in the interval, but X naught can never equal L. So I'll let you think about that. It's, just some straightforward trigonometry, but based on the bounds on X sub 0 and U, for this case, the only root of the denominator is at 0. So now I'm going to take a look at the limit approaching 0. Okay, for the limit, I'm going to use some shenanigans. And so here, let's go slow again. I say, since U plus X naught is between negative L and L. So how the heck did I get that, right? So if you start from here, this says, U is in between. So you've got minus, so that's the X sub 0, and then here's U. And then it's less than or equal to L minus X sub 0. So what I did now is for the next equation, I just moved this x sub 0, move this negative x sub 0, this one and this one, move them both inside. Then you get u plus x naught is between negative L and L. So if u plus x naught is between negative L and L, stay with me. You're doing so great. We've just got like, I think one more slide. You're doing so awesome. Here, we're inside the interval. Inside the interval, you know, the function and the periodic extension are the same. And so here, what I want to do is I want to replace this f that we have in the numerator that we got from the partial sum or something. I can't remember where we got it from. I want to replace that with f tilde from the Q function, from when we rewrote the partial sum and the target function as integrals using the Deflate kernel. You remember all that? Yeah. So I replaced that with the periodic extension, and now just take a limit. You know, send Q to 0. So here u is the variable. Be careful, u is the variable. So in the numerator, when u goes to 0, I get f tilde of x naught minus f tilde of x naught. So this entire numerator term goes to 0 when you take the limit. So this goes to 0. And similarly, the entire denominator term, when we send u to 0, that goes to 0. So I get 0 over 0. And you remember Calc 1, so we can use L'Hopital's rule. Remember, f tilde of x naught is a constant. This is a constant. So I'm only taking the derivative of this function with respect to u. So f tilde prime u plus x naught times 1. I have to do derivative of the inside chain rule, but derivative of u plus x naught is just 1. And then downstairs I have, you know, chain rule derivative of sine of 2 pi L u, right, times 2. And then apply the limit. This time the limit exists. You send u to 0, we get f tilde prime of x naught, and cosine of 0 is just 1, so the cosine term disappears completely. At the end of the day, we don't care what the limit is, we just care that the limit doesn't blow up to infinity. So what we've proven is that inside the interval minus L to L, the function Q of u does not have an infinite discontinuity. You know, that's what, and here this is a two-sided limit. So in fact, we've shown there's a removable discontinuity at u equal to 0. So Q of u is piecewise continuous. And there's actually a weaker version of the Riemann-Lebesgue lemma that could kick in right now, but you know, I don't know why, for some reason I'm gonna go a little further. But yeah, so here we've done it for case 1. So now case 2 is very similar. We just get one more root in the numerator. So let me show you case 2. Now we assume x sub 0 is on the endpoints of our interval, closed interval minus L to L. And let's just pick, you know, the argument, whether x naught is equal to L or x naught is equal to negative L, it doesn't matter. The argument is the same. So without loss of generality, I'm going to just go ahead and assume x naught is equal to negative L. So our interval that u is in, so remember we're integrating u from minus L minus x naught to L minus x naught. So in this case, we're integrating u from 0 to L. To 2L, excuse me. We're now, in this case, integrating u from 0 to 2L. So now we want to check what are the roots of the denominator. You know, where is sine of pi over 2LU equal to 0 in this interval? In this interval, it's 0 at the endpoints. It's 0 when u is 0, and it's 0 when u is 2L. We've already dealt with the case when u is 0. The only difference here, instead of doing a two-sided limit, because this is at an endpoint, we would have to do a one-sided limit. It would be a limit approaching from the right. But because of the periodicity, you know, we can basically just use the work we did before. And by the periodicity, we can equate the limit from the right to the two-sided limit. And that limit existed. We proved this limit existed on the previous slide. And here, the limit from the right is equal to the two-sided limit, which exists. So at u equal to 0, there's no problem. We know there's a removable discontinuity. In particular, there's no infinite discontinuity. Finally, last but not least, at 2L. So, you have to remember there's periodicity kicking in here. So when I take this limit going to 2L, just keep in mind that f tilde x naught plus 2L, this is a 2L periodic function, will have the same y value as f tilde of x naught. So how does that come into play? So it's so that we can use L'Hopital's rule. So now look, I'm sending the limit from the left because we're in, it's at an endpoint. So I'm sending the limit from the left. So here, this u right here becomes 2L. So that becomes f tilde of 2L plus x naught. But f tilde of 2L plus x naught equals f of x naught. So I get basically f tilde of x naught minus f tilde of x naught in the numerator. And I get 0 in the numerator, 0 in the denominator. So I can use L'Hopital's rule. So here, this term now goes to 0. And in the denominator, of course, sine of 0 is 0. And so now we can use L'Hopital's rule. Remember, f tilde of x naught is a constant. This term right here is a constant. So you take the derivative, you get f tilde prime, u plus x naught, replace the x naught, the u, with 2L. So my limit is f tilde prime 2L plus x naught times minus L over pi. We could stop here. I went one more step and used the periodicity. Again, if the function is periodic, its derivative will be periodic. So by periodicity, again, here I could replace it. And really, the thing we care about here is that the limit's not going to infinity. That's the thing we care about. Other than that, we don't really care what the limit is, just that it's finite. So we've proven now Q of U is piecewise continuous in either case, whether x naught is in the interval or at the endpoints. So I won't go into the details of the derivative, but I'll just say that by quotient rule, we can just claim that when you take the derivative, we have a quotient of piecewise continuous functions and, or even piecewise smooth actually. And so, we can conclude the derivative is also piecewise continuous. And therefore we can conclude the original function is piecewise smooth. So having said that, if you accept that, then by the Riemann-Lebesgue lemma, remember we wrote so I should add this or something. We wrote the partial sum of the Fourier series evaluated at x sub 0 minus the function f evaluated at x sub 0 is this integral right here. This integral is the partial sum minus its target. And so by the Riemann-Lebesgue lemma, that limit goes to 0. So, we've basically shown this, that difference goes to 0 as n goes to infinity, which we can write in limit form, like this. And remember the partial sum here, that's the Fourier series. That is the Fourier, so I just replaced it. So, if we start with a piecewise smooth function, then the Fourier series will converge, number one. And number two, the Fourier series will converge not to the original function, but to the periodic extension of the adjusted version of the function. So now we sort of have some kind of, technical appreciation for what a Fourier series is and what it's doing, at least in the case of when you're dealing with piecewise smooth functions. So that ends the pointwise convergence proof. Of course, you're not going to be asked to reproduce the proof on a test or anything like that. It's a very common thing in a math class or analysis class to go through very difficult detailed proofs. That's just how we learn in for math majors. I mean, in my analysis class, we had to go to the board and do the proofs in front of the whole class. And that was great because, you know, everyone loves that. But, you know, it's a good way to learn. Yeah, but of course we should know the result. We should know the result. And we'll have a stronger result. So we'll talk about different types of convergence. So here we talk about pointwise convergence. So let me talk about uniform convergence. So this is the final lecture on the notes on Fourier series by Seeger. And so this is the conclusion of our analytic discussion of Fourier series. So now we have a good technical appreciation for what a Fourier series is, when it converges, and what it converges to. So this is kind of now some little itty bitty nitty gritty details about the type of convergence. So here I want to introduce this notion of convergence known as uniform convergence. So in Calc 2, when you studied sequences in series, the type of convergence we studied there was called pointwise convergence. We didn't necessarily use that term in Calc 2, but that's what it was. For each point X, we were able to show the Taylor series or Max series would converge. So here we want to sort of introduce a different notion of convergence, okay? So the Fourier series, of course, can be thought of a sum of functions, right? Here, obviously, cosine n pi x over L, sine n pi x over L, those are functions and we're summing them. But for a fixed value of x, if we choose x, then they become constants and we get a regular series. It's just a sum, an infinite sum of constants, okay? So the Fourier series star up here. So when I say star, I'm referring back, to this formula. So the Fourier series above there, we say converges pointwise to some target function t of x, t for target. So this is an epsilon delta proof sort of. So, hang in there. Don't worry about the epsilon stuff. If for every epsilon greater than 0, and this part is important here, and each x sub 0 in the interval, there exists a positive finite integer n sub epsilon of x naught. So hold on. Here, what's with all the notation? So this, really, I could have just written capital N. I've just added the epsilon to indicate this is the capital N that goes with this particular choice of epsilon. Because we can choose epsilon as we want. We can choose epsilon to be 1/2, 1/8, 0.0001. And for each epsilon and for each x we choose, there's going to be a capital N. So the capital N we're choosing depends on our choice of epsilon and x. Okay, so epsilon, you can think of epsilon as a tolerance for how closely we want it to converge, and the x sub 0 is a location. So here the capital N is dependent on the tolerance as well as the location. So how accurately it converges will not just be dependent on our choice of tolerance, but in this case, will also be dependent on where we're looking at the point, at the function, the actual, location on the domain. So, and so pointwise convergence says if, we're sending a limit, we're sending n to infinity. So if the number n that we're sending to infinity, if it's bigger than this specific integer, n sub epsilon, which goes with our choice of tolerance and our choice of location, if n is bigger than that number, then our partial sum will be within the tolerance to the target. So here, you should see this as like a distance statement. So this is saying the distance between the partial series and the target is less than this tolerance epsilon. And of course, what we're expecting to see is, as n gets bigger, as epsilon gets smaller, n will get bigger. As n goes to infinity, epsilon goes to 0, and we get convergence. That's essentially, that's what this definition implies. That if you make epsilon smaller and smaller and make n bigger and bigger, you'll have convergence. This inequality will be always true, as long as you make n bigger as you make epsilon smaller. So this is pointwise convergence. And the issue, why do we say pointwise, is because the location comes into play. This caveat here, where we're saying it's not just the tolerance here that's going to determine how many terms we use, but it's also the location that's going to determine how many terms of the Fourier series we need to use so that you fall within the given tolerance. And so we contrast that idea with the notion of uniform convergence. So here, you specify the tolerance epsilon, then for that tolerance, there exists a number n sub epsilon, and if we use more than n sub epsilon terms in our sum, then our partial sum will be within the tolerance of the target. Here, the choice is not dependent on x. So here we say this is true for all x. I mean, that's, here you should look at where the variable x comes into play in the definition. Here it shows up before we choose epsilon. This is before we choose epsilon. In the uniform convergence definition, it's after we've chosen epsilon. So the uniform convergence says the convergence behavior only depends on your choice of epsilon and how many terms you're using. It does not depend on your domain location. So did I just go backwards? So yeah. And so, we can think of pointwise convergence as implying that the absolute value of this difference, the partial sum of the Fourier series and the target, that goes to 0 as n goes to infinity for each x. So here it's, the choice of x comes into play. Pick an x, then take the limit. Pick an x, then take a limit. For uniform convergence, we're saying the maximum distance. So here we're saying every point for every x value will always, as n goes to infinity, will always be within a certain tolerance. So there'll always be a certain, tolerance level that they're all within, and they'll all be within a certain amount of accuracy. So, this is kind of abstract stuff, and let me show you an example. This has nothing to do with Fourier series specifically. This is just an example from analysis, okay? So this is an example of a sequence of functions that converges both pointwise and uniformly. Okay, so let's just go slow. So the function, so for each n and each x, so never mind about the x part. So for each n, we have a function. So for example, if n is 1, I have x plus 2 over 4, which is a function you can graph. If n is 2, f sub 2 equals x plus 2 over 8, so on and so forth. And then if you fix x, so now here, and I've graphed here a generic, and here you can see what happens when x equals 2. Regardless of the function, when x equals 2, you get the y value has to be 1 over n. So here, if I plug in x equals 2, you get 2 plus 2 is 4, 4 over 4 is, so regardless what the function is, when x equals 2, the y value is always 1 over n. Okay, where n can be 1, 2, 3. So you see that the height gets lower and lower as n goes to infinity. And so here we claim it converges uniformly to 0. So here I've graphed 0 here on this is the target function here in green. It graphs uniformly and pointwise. And so here for pointwise convergence, it's very easy. You can just take a limit. So pick any x sub 0, pick a point, plug it into the function, take the limit. We know if the numerator is a fixed constant, which it is, here x sub 0 plus 2 is a fixed constant. We know if the denominator blows up to infinity, the sequence is 0. And so here we've shown, what have we shown? If you pick an X value, so if I pick an X value down here, then go to the corresponding point up here on the graph and send n to infinity, that's going to converge to 0. And so if you pick a X value, send infinity, that's going to go to 0. That's what we've proved with the pointwise convergence. If you pick any one of them, send n to infinity, that point's going to go to 0. Okay. For the uniform convergence proof, and I'm going to motivate it with the graph. From the graph, you can see that for every X value, the maximum distance is 1 over n. We can see that any X value you pick, it'll always be less than this distance away from the x-axis. So here I can claim that the maximum vertical separation, the maximum height between fn of x as a function and the target h of x is always less than 1 over n. Here, this is true for any function that I pick. If n is 1, if n is 2, if n is 10, 10, oh, that was terrible. If n is 10,000, no matter what value of n you pick, it's always true that, f of absolute value, f of n of x minus h of x will be less than 1 over n. And so here, I can show the limit of all the points. That's the big difference here. With this, when I do the max, here we're showing that if you, at every x value, the function is converging to 0 in mass. They're kind of going uniformly together and collapsing to 0. And so, of course, the question is, well, why wouldn't that always happen? When would that not happen? So analysis is all about counterexamples, right? Just when you think something's true all the time, there's someone sitting there working diligently all day and night just to come up with a counterexample for what you believe is true. That's basically what analysis is. So here's the counterexample. And I won't be able to finish this example today, but this is pretty much the hardest slide, we have to talk about for today's lecture. I have 4 minutes, so let me talk about it a little bit, but I'll pick it up here next time. So the function, it really helps to just pick an n value. So if you graph the function, pick an n value, graph the function, it has this kind of tent shape. Okay, so we're defining it from -2 to 2 from, for each n, you can show me 0 here from -2 to 0, and then it'll have this sort of tent shape from 0 to 2. For example, if you pick n to be 1, so let me just cover up this n here. Let's just suppose n is 1. Then I'll have from 0 to 1, I'll have the function x, 0 to 1, I'll have the function x, and then from 1 to 2, you'll have the function 2 minus x. So it would look something like this, like 0 to 1, and then 1 to 2. That's when n is 1. And that'd be 0 for all other functions. And then as you make n larger, it kind of starts to collapse. Here, you should see this going this way. Think about what happens to 2 over n as you send n to infinity. As you send to infinity, the triangle function kind of collapses, kind of like an elbow closing, So in here, this triangular part is going to get narrower and narrower. The other part's also going to move. This part's also going to simultaneously be moving. When it converges, it'll completely, you'll just have a solid line and there won't be anything. It'll just be completely equal to 0. So here, and I'm going to stop right here in 1 second. Here, we can show the function converges pointwise to 0, but it does not converge uniformly to 0. And very quickly, why not uniformly? And I'll start here next time. But basically, this counterexample is set up so that no matter what n value you pick, remember n is going to infinity. N will never actually equal infinity. So this number 2 over n and 1 over n, they're approaching 0. They'll never actually get to 0. So the way this is set up is no matter what n value you pick, there will always be one point that's exactly 1 unit away from the target function. Even though you sent n to infinity, n could be 10 billion, and every point but one will be super close to the target function, but there'll be one point that's exactly 1 unit away. But when you send n to infinity, infinitely many of the points will converge. That thing collapses to 0. The size of the interval collapses to 0. When you send n to infinity, this interval collapses to 0. This interval collapses to 0. There is no function. You just get a flat line. So you do have convergence, but it's not uniform convergence. All right, everybody. I will pick it up with this weird counterexample next time. And again, don't worry about this counterexample. This is just one example to illustrate the idea of uniform convergence. Then we're going to go back to regular Fourier series. Okay, so this is just a nice little thought exercise to illustrate pointwise convergence versus uniform convergence. All right, so let me just stop right here. And I thank you for your time, everybody.